Okay, so this question is asking you ultimately to find our end goal. Typically is to maybe find that little distance right there. Okay. Now, in order to do that, we have to realize that there are multiple triangles here. So one thing that I like to do, and you're going to have to do this, especially the triangles that are overlapping, is to separate them. So I'm going to separate this small one, and so that's the 45, 45, 90. And then we'll look at the larger one, the 30, 60, 90. And pull that apart. And off of what we've been told in the problem, and obviously that is recaptured in the picture here, is that this is 45 degrees. It's a right angle, making that 45. They tell me that that is 9. This is 30 degrees. This is a right angle. This is 60 degrees. And I know absolutely nothing about that right triangle in regards to the side lengths, correct? Okay. If I'm looking at a 45, 45, 90 as a template, and I'll do this in, let's see here, we'll do it in pink. In a template, this side would always be your smallest side. This is the same thing. And then this side is always n radical 2, or the smallest side times radical 2. Is that all right? So right here, if my template and my actual triangle that I'm working in are congruent, which that's the way we're going to build our template, those two numbers should be equal, right? Or those two expressions should be equal. So if those are equal, this gives me n radical 2 is equal to 9. So then n would be 9 over radical 2. I just divide both sides by that radical 2. That's the coefficient over here for n. I think it makes sense right now to rationalize that. So it gives us 9 radical 2 over 2. That is what n is equal to on this 45, 45, 90 triangle. So this side length here is 9 radical 2 over 2. And this side length here is 9 radical 2 over 2. Is that okay? Now that I've got that, let's look at this red triangle real quick. Because remember, this red triangle was stacked on top of this green one. Is there a segment that they share completely? Don't they share this bottom segment completely? So what's that make this length right here? 9 radical 2 over 2. Okay. Now, if I'm working in a 30, 60, 90 triangle, across from 30 degrees is your inside. It's a bad green. So that's your inside. Okay. What is this side over here referred to as in a 30, 60, 90? That's 2n. So if this is n, then 2n would just be double that, right? If I double something with a denominator of 2, don't they just cancel the 2's? So 2n is going to be 9 radical 2. And now this side here is what compared to n? What do I multiply that side by? Not radical 2. That's my n radical 3 side. So if n was 9 radical 2 over 2, then we'll multiply that by a radical 3. And that's that answer. You type that in, it's going to tell you you're wrong because of simplification rules. I want to multiply the radicals together up there, so it's going to give me 9 radical 6 over 2. And that is that length of that right triangle. So right here, we've got this distance, this green distance here, being 9 radical 6 over 2. And then we've got this distance here being 9 radical 2 over 2. What do I do with those to find this overall distance? Well, think about this. If I add them, that would be putting the green one on top of the purple one, right? Like stacking them? I'm going to subtract them. So I'm going to take 9 radical 6 over 2 and subtract 9 radical 2 over 2. Okay? And I think on Friday we talked about how, because these are different radicals, they're we kind of view them as like, if I asked you, do you know what radical 6 is, what exact number that is? If I asked you what exact number radical 2 is, they're kind of unknown to you, right? And they're different, so maybe we could view one as it being, like a radical 6, we just say that's x. And radical 2, we say that's y. And if I said, well, what's 9x minus 9y, could you make that one concise expression? And you can't, because they're different variables, right? They're unlike terms. So 9 radical 6 and 9 radical 2 are unlike terms as well. Therefore, that's the exact, fully simplified answer. You could maybe, because they have the same denominator, if you wanted to, you go 9 radical 6 minus 9 radical 2 all over 2. But either one of those versions would be fine. Math Excel asks you to type in as a decimal, which makes it easier for you. But and this is the approach I want to take throughout the rest of the year. Throughout the rest of the year, one of the main kind of byproduct topics that I want to talk about with you guys, other than obviously the mathematics and learning the actual geometry, is rounding error. Okay, and how rounding error can then be compounded in other calculations. Okay, so if I were to take this blue distance and round it to whatever it is, maybe to the 10th place, but then use that distance to find an area later on, that area is going to be off. Does that kind of make sense? Because I use a rounded value in it. I'm going to kind of explain to you as we go through mathematics, you go through science as well, and this is in particular why in science you talk about sig figs quite a bit. I want to make sure that if they ask me to round this to the 10th place or the 1000th place or the 100th place or whatever, that I find it as an exact value first, type it in my calculator, and then my calculator will tell me that I am accurate out to however many decimal places. So kind of what I want to do an example of what I mean by that real quick with you. If I were to take we did all this work without ever changing a radical to its decimal version, right? So when I get 9 square root of 6 minus 9 square root of 2, all of that over 2, right now, we can be guaranteed that that number right there is 100% a 1. Okay? That make sense to everybody? Okay. Now, I'm not sure, based on how calculators work, I'm not sure if that's a 2 or not. That number that I've highlighted is all predicated on the number that comes after it. If the number after it is less than 5, then that would be a 2. Does that make sense? Okay. But if the number after it, maybe the number after that decimal place is 5 or bigger, that could have actually been a 1. Does that make sense? So your calculator is actually potentially rounding that 2 and keeping it a 2 based on the number after it, or it could have actually been a 1 and your calculator is actively rounding that up. Does that make sense? And it's all based on that number beyond that we don't know what it is right now. Okay? If we were to, just because I have the ability, might as well try this real quick. Go to algebra, rounding. I can go out to 13 or 15 decimal places here. So let's go 9 times square root of 6 minus 9 times square root of 2. And we'll divide all that by 2. So right there is that decimal place right there. So you see where my cursor is? That's actually a 1, right? Okay, because the number after it is an 8, and that's why Desmos rounded it to a 2. Okay, so you guys talk about precision in our science classes, right? Okay, this tool is only precise out to essentially that many decimal places. Okay, where GeoGebra is precise out to that decimal place where my cursor is right now. Because again, I don't know what that 4 is. Okay, if it should be a 4, if it should be a 3. That being said, it's not a huge deal, but if they ask me to round this to the 10th place, and I know that I did all my work and these are exact values, I can be guaranteed with 100% certainty that that should be a 6, and that should be a 5, and that should be an 8, right? Does that make sense? Where if I were to, let's just be really foolish with this. Let's say that when we found this distance here to be 9 over radical 2. Okay, so maybe we did something like this. Let's say, now let's say this is overreacting a little bit, but if I go square root 2, is that number right there? Let's just say it's 1.41. You guys agree with that? So let's go 9 divided by 1.41. I get that number there. Okay, so that number there is this length here. Is it okay with everybody? Okay. Now, if I want to find this length here, all right, I'm going to multiply that by radical 3. So I'm just to show you just how drastic one rounding error can happen. So I'm going to leave the radical 3 as radical 3. So go s times square root of 3 would be this red distance here. Is it okay with everybody? Okay. Well, now I'm going to take that distance and subtract from it the 9 over radical 2. So I'll take, let's call this r minus 9 divided by square root of 2. Gives me that number right there. So you get 4.6916. I only rounded one value, correct? Only rounded one value. But let's see, just so I'll cut this out and I'll move it up so you can see a little bit better. I only rounded one value, and you see now that we are off in the hundreds place by quite a bit. Does that make sense? Okay, that's called rounding error. Okay, so if I know that impact of rounding error on calculations, then I want to mitigate that rounding error. I want to minimize it. Okay, if I can, I want to completely cancel it out and make sure it never happens. So what I will do with you in class is I will make sure that we do as much as we possibly can with exact values. Especially if the question asks us to round to the hundredths place, thousandths place, or whatever in Math Excel, we will do everything with exact values, get an answer that way, and then turn to my calculator, because then I won't be guaranteed out to being 9 decimal places or whatever my precision on my calculator is, that I will not be wrong in Math Excel or the Ohio end of course test because rounding error was present. Does that make sense, everybody? People always ask, well, why we gotta do this? Why can't I just change the decimals? That's the reason, and I think that's a huge thing for your science classes as you move forward, and it is extremely important as you take higher level math courses. Okay? Obviously, it's much easier to change things into decimals and do all the operations with decimals, and that's what we want to do because that's convenient for us. It's what we feel like a safe thing to do, but it produces error in accuracy. Okay. I want to do a couple practice problems with you, if this will load. Day and Friday. So just real quick, let's go through. Let's go through number 3 here. Okay. If we were to take our template, where this is a 45-degree angle, this would be in radical 2. If we were to slide this over on top of this one, what 2 parts match up to where you develop an equation that is solvable? Okay, in radical 2 lands on 12, right? Okay, that's going to allow me to solve the equation for n. But also, doesn't x land on n? So in this equation, when I solve for n up here, because of this overlap down here, it shows me exactly what x is going to be, right? And that's what I'm actually interested in the problem. So what do I need to do to solve for n here? Yeah, divide by radical 2. Okay. Now, and I just want to make sure that we understand this. Radical 2, we just typed it on Desmos, and it gave me 1.414, right? So really, when I say n radical 2, when I say n radical 2 equals 12, I'm also saying this idea, that 1.414 times n is equal to 12. Does that make sense? Now, it's not exactly, because I rounded this number, so when I solve for n, when I divide here by 1.414, divide by 1.414, that's going to give me my value of n, okay? But because 1.414 was rounded, there's going to be a degree of inaccuracy with what n really is, okay? But over here, because I didn't round either of those values, 12 or radical 2 is not rounded, will there be inaccuracy? There's no rounding, right? So that's going to be an exact value. I'm going to rationalize this by multiplying by radical 2 over 2. Radical 2 over radical 2 gives me 12 radical 2 over 2, right? Okay. Now think what that really means. If you look back here real quick, what that really means is, so 12 can be written as 2 times 2 times 3, right? That's what 12 is, prime factorization. Radical 2 is 1.414 all over 2. What cancels here? These 2's right there cancel, right? Okay. And those 2 cancel right there because that 2 was a part of the 12 that was there, right? So what I'm trying to show you here is that those are the only things that can cancel. The number out for the coefficient of the radical in this denominator, because that factor is not like this denominator, right? Okay, so it can't cancel. And that's what a lot of people want to do, is that they ignore the symbol here with the radical and think that everything can just cancel because there's all a bunch of 2's. The only thing that can cancel here is that 2 and a 2 that resides in that 12. So it gives me 6 radical 2 as an answer. Some of you might be seeing patterns. Okay? If this was 14, what would that answer be? 7 radical 2. If this was 18, what would that answer be? 9 radical 2. If this was 20, what would that answer be? 10 radical 2. It's half. If they start you with this as an, basically it doesn't even matter if it's even. It's just easier if it's even because you get a integer back. But half of this times radical 2 is going to be your side length. Okay? That's because each time we're dividing by radical 2 because of the structure of these triangles. Is that all right with everybody? Okay, so let's do then. Why don't you guys do number 5 on your own? All right, so if you take your template and now make sure that your 30 degrees are going to match up. Okay, so across from 30 degrees, what would this side over here be on my template? N. And what is this one going to be? Careful. This is 2n. And now, across from 60 is the n radical 3, right? So when I put them on top of each other, okay, if they're drawn to be congruent, what matches up? 2n and 13, right? So there's your equation. 2n equals 13. Therefore, n is going to give me 13 seconds, 13 halves, 13 over 2. Don't write it right now as like 6.5, okay? Because that removes a fraction, and when we want fully simplified, usually the rules for fully simplified mean no decimals, okay? So now that's n, which would be this side right here, correct, in my template? Okay, and then we say n, and when we overlap, n equals x, right? N and x are the same thing? So the distance I'm looking for here would be 13 over 2. Is everybody okay with that? Now, I know I didn't ask you for this, but it's a quick alteration to this to find y. What would y be? Good. 13 over 2, and then times radical 3, right? Now, I think we talked about this last week as well, but it's a point of confusion for some people. I'm going to write this kind of like what you wrote things in like first grade. If I have 13 over 2, and I'm going to put radical 3 kind of right there, okay? You can write it that way, all right? However, this is a rational number, okay? This can be written, I don't want to say as a rational number because it can't, but it can be written as a ratio. Does that make sense? Okay, so now I have a fraction times a fraction, correct? When you have a fraction times a fraction, how do you multiply those? Just straight across the top and straight across the bottom. Okay, so what does that generate? It creates an alternative look for that amount, right? But it is the same thing. 13 over 2 times radical 3 is the same thing as 13 radical 3 all over 2. Okay, you will see us transition back and forth between those two notations. And the assumption is because we learned how to multiply fractions in 5th, 6th grade, that they can do that without any discussion about why they do it, okay, or how they do it. Let's do, so the questions that I think that get very problematic for students are ones like these, okay? Give you a minute to draw that, and once you draw it, we'll then reconvene and talk about it real quick. All right, so looking at that, we need to decide, where do we start? Where do we start? Do we start directly trying to find x, or do I have to navigate around, find several missing values before I can get to x? Okay, So the question is always, when there's multiple triangles, where do I start? Start in the triangle that you know the most about. Which of those two triangles, and when I say most about, it's usually referred to as which one do you know the most distances for? You know more about the top one, right? So what I'm going to do is I'm just going to get rid of that bottom one. Okay? And all I've done here is just whited out that bottom one. And now I've got a problem that is just like the ones we've already done, right? Across from 60 is always what side? N radical 3 side. Okay? So what's that allow me to solve for here? What is n going to be? N is going to be 9. 9 should then go across from what angle? Should go across from your 30, right? So 9 should go here. Now, what should this distance here be? 18. Is that okay with everybody in that triangle? Okay. So now, we'll bring back this triangle, and we have done enough work to basically say that 9 radical 3 transition to the 9, but the 9 then transition into that 18, and now I've got that for this triangle. Does that make sense? What side is that in a 45, 45, 90 triangle? That's your n radical 2 side. So now, maybe using some of the patterns that we've seen in the past, or we go through the direct algebra, what's n going to be? It's going to be 9 radical 2. Okay, it's always half that number times radical 2. And the way we can confirm that, if I multiply this by radical 2, don't I get 18? I get 9 times radical 4, which is 9 times 2, which is 18. So that is then the x that we were interested in. Does that make sense? So when you see these problems where we've got figures staggered on one another, stuck to one another, start in the triangle that you know the most about. Okay? The way I like to do it is I redraw them. So if I was doing this on paper and pencil, you're going to see maybe 3, 4, 5 drawings, depending on how many triangles I have. And I just regenerate a new problem inside that overall problem. Okay? And it makes it easier for myself. Okay? And that's really what I do in all mathematics. I'm not saying it's the right way, but if I could take a collective problem and break it down to 3 or 4 or 5 simpler individual problems and deal with those 3, 4, 5 simpler individual problems, then allow the solutions to those to build to my overall problem, that's what I'm going to do. Does that kind of make sense? Okay. Give you an example of that in context of something that you have absolutely no experience with. Okay. So this morning in stats, we're talking about some things here. We've got a pretty nasty formula in stats. Okay. This thing here is what we call a confidence interval. Okay. There's a lot of stuff that goes into this. Okay. And basically what I told my students is, okay, I'm not going to worry about memorizing this thing. Okay. But I'm going to come down here and I'm going to do one thing. I'm going to find out one value out of that thing. Okay. Break it down to one problem here. Okay. One smaller problem. Okay. Then here is a second smaller problem. Okay. And these are easier than the overall individual problem. Does that make sense? Okay. Then I start plugging things into my formula, and it makes the process so much easier. Okay? So if you can realize, okay, this is a overarching concept, break it up into 2, 3, 4 smaller problems, it will make your life so much easier. All right? So take a minute, see what you come up with on that one for X and Y. All right, so working on this one, the triangle that you know the most about is which one? The top one, right? So if I look at that top one, get rid of this garbage, can you find all the parts of that top one? Oh, there you go. Can you find all the parts of this top one? What would this segment right here be? 6. And what is this one going to be? 6 radical 2. Okay. So now you have transitioned into this bottom one, right? if I transition into that bottom one now, I know you can't, you guys don't have the ability to erase like this, but you could redraw. I get down there, now what is X going to be? This is a right angle here. Even though it's not drawn, we know that's a right angle, correct? So doesn't that have to be 6 radical 2? And then what do I do with the 6 radical 2 to get Y? So 6 radical 2, careful. Remember, because this is n, this is n, this is n radical 2, right? So I take 6 radical 2 and I multiply it by my radical 2. So it's going to give me 6 radical 4, which is 6 times 2, which is 12. Is that okay with everybody? All right. Now, something that, and this is what you heard me back here scrolling through stuff. We work on these special right triangles for multiple reasons. Okay. One, it's a true relationship. But as we work through other content, other areas, if they're going to give me a triangle to maybe work with like a pyramid or something like that, the triangle they're going to give me is going to be a 45, 45, 90 or a 30, 60, 90, just for the fact of getting you more exposure at working with these types of things. Okay, so I was just trying to scroll through some of my notes from previous, or not previous, for upcoming sections. Okay, so this is an area formula or an area section for parallelograms. Notice in a parallelogram, I need this distance here times this height, and we'll talk about this length here. But notice the only way that I can find that distance right there, that H, is over here in this 45, 45, 90 triangle that they give me. Does that make sense? Okay. I would argue, so right here you can see we've got some work with the 30, 60, 90 in finding the area of this thing. Nothing there. A lot of rhombus stuff. Here's finding the area of an irregular shape at this point. We will have another formula for this, but that 30, 60, 90 triangle right there, find this length of 2. So in 10.1, that's necessary. We get to 10.2, areas of trapezoids, 60-degree angle right there. So it's probably talking about a 30, 60, 90 triangle, 45-degree angle. Okay. So in order to understand these other topics, we're going to have to deal with 30, 60, 90, 45, 45, 90 triangles all year long, or for the rest of the year. Okay. Here's finding the area of a regular hexagon. In order to do this, we need to know this little triangle on the inside here, and that little triangle is going to have a 30-degree angle in it, and it's a right triangle, so 30, 60, 90. There's just so many different applications. You'll see them a lot in try. So here's some circle work. If this is kind of, we call this a major arc, it's 240 degrees. So this black arc right here would be 120 eventually. Okay, and down the road, I'm going to ask you, what is the area of that triangle right there? Okay, that's called a actually, I'll ask for that area of that triangle because I'm interested in like this slice of this circle. We call it a sector. Okay. Well, what happens is that when I draw that distance right there, this angle right here is 120 degrees. Does that make sense? Well, if I cut that 120 degrees in half, isn't that triangle right there now a 30, 60, 90 triangle? Does that make sense to everybody? Okay. So there's a lot of stuff that we are going to visit and talk about with 30, 60, 90, 45, 45, 90 triangles in the near future. Okay. Now, if you are a person that's going to go, you're going to go to Algebra 2, then you're going to take trig. Something we talk about in trig that it just allows, it's basically a calculator for us, like a static calculator. What's called the unit circle. And it just talks about distances and so it's in the coordinate plane, all that kind of stuff. But these ordered pairs here, Okay, and that number right there, so pi over 6 is equivalent to 30 degrees. Okay, and then these distances right here for this ordered pair are created off of 30, 60, 90 triangles. Okay, so the number one tool that we use in a trig course is based off of 30, 60, 90, 45, 45, 90 triangles. If I were to list maybe the top 3 to 5 topics of most importance in high school mathematics because of how much they're used in other courses, one of those top 3 or 5 things is going to be 30, 60, 90, 45, 45, 90 triangles. Okay, structural right triangles. They have such a great use beyond this class. So I'm just trying to open your eyes to the idea that they're going to be around. Okay, so if it's something that you're struggling with, make sure that you reach out, you use the resources that you have to eliminate some of that struggle, because they're not going to go away. All right. I wish I would have known that when I was in school, that they're not going to go away. I would have initially learned them a little bit better the first time. Radicals also. I know some of us are struggling with those and don't like those, and I agree. When I was in school, radicals blew my mind. Hated them. Okay, avoided them. Never got good at them though. Okay, they're not going anywhere. Okay, so make sure that we understand that and we get those two things fixed if we have personal struggles with them. I'm going to send you guys in an email here briefly the rest of this worksheet, and I will post a math Excel to go with it. Now, if we read this, it says, leave all answers in simplest radical form. It says this means that if you develop a radical throughout your work and it is part of your answer, you need to reduce the radicand and write your answer so the radicand does not have a perfect square residing in it. So if I have like radical 12, I need to rewrite that as 2 radical 3. Says these will result in exact values for answers. Every now and then your work will make radicals disappear. That is fine. But your answer will then just be a rational number. So if I had, for whatever reason, like a radical 3 on top and a radical 3 on the bottom, they cancel out. And I'll just have my rational number as my solution. But what you're going to do is leave those in simplest radical form. And I will, so I'm going to send this out in an email right now. And then I will also email you once I have the Math Excel companion to this uploaded, and you can type your answers in, okay? But you'll have at least until, what is today? 1st, at least till midnight on the 3rd, if not longer, to get this finalized, okay? So I'll send that out now.